Okay, so let's get started. Good. All right. Okay, so today we will talk about a different topic from what we were doing last time. We had a discussion of middleware systems. So that part is done. Today we'll talk about security, and then we have one more class on Wednesday where I'm going to start wrapping up the course. Okay. So if you already taken a class on security, some of these concepts might be familiar to you, but under the assumption that you may not have, we are going to look at security topics, but from the lens of distributed systems. We are not going to look at basic concepts like encryption and things of that sort. I will explain a little bit what they are if you don't know, but you probably at least have a concept of what they mean. So the idea here would be to understand how these issues apply when you have distributed application. Okay, so first of all, why is this topic related to distributed systems? So if you remember, our definition of a distributed system is it's a set of independent computers that are connected on via some communication medium that are running some application component. So since the applications that are running in your systems are accessible over a network, they're accessible to legitimate users of that application as well as adversarial users, maybe hackers and things of that sort. So we need to think about how to ensure that your application, whatever you're building, is not going to be vulnerable to security problems. Okay, so in the context of this class, we are worried about three specific problems. One is you want to protect against invalid operations, which means that you don't want users to perform operations that they are not allowed to. So for example, your web application may have certain methods that are only accessible to admin users and other RPC or REST methods that are accessible to normal users. You want to prevent ordinary users from accessing some of those operations. Okay? You want to, so that's unauthorized. There's of course invalid, which means that you probably make a call that doesn't even make any sense. So that's something you want to protect against. It might cause other problems like buffer overflows and things of that sort. And then the last one is to protect against unauthorized users, which are users that are not allowed to access that service. Okay? That's a very high level set of ideas. What we are going to look at is how are you going to go about addressing some of these topics. Okay? So before I do that, I just thought I'll add a slide to explain the difference between security and privacy. You remember, I think it was exam 1, where there was, or maybe 2, I can't remember, exam 2, where I had a question on private cloud, and a lot of the answers were given from the perspective of security attacks, okay? Even though the question was about privacy. So I just thought I'll say a few words about security and privacy. They're of course related concepts, but they're distinct concepts. Okay? So if you think about unauthorized access to a machine, let's say somebody gets access to your machine, okay, or some server, and once you do that, then you have access to resources on that machine. Specifically, you can access files or data that's stored on the machine. So if somebody hacks into a machine, steals data, okay, that's clearly a security problem. Okay, even though the data may be sensitive, you may have credit card information, personal information that's stolen. Okay, at the end of the day, that was a security problem. Of course, private data has been stolen, no question about that, but this is considered more of a security issue than a privacy violation. Okay? And to understand now the difference between the two, so clearly that security violation has caused loss of private information, there's no question about it, but it's still considered a security problem. Now, there are privacy violations that have nothing to do with security, okay? Just so that you understand why these topics are different. So here are some examples. Okay? You have a phone that runs mobile apps. Okay? A lot of these applications collect information. Okay? Specifically for advertising reasons, many of these applications are going to collect location information. Okay? So the application has now collected a log of all the locations you're visiting over the course of a day, ostensibly to give you location-aware advertisement. So maybe if you go to a restaurant, you get an ad for a restaurant or a coupon. That's the basic rationale, but they're getting a lot of information as a result of collecting this information. For example, they can see that you visited a doctor, right? Because you showed up at the doctor's office, even though that's an unintentional leak of your private information, because that's not what the application needs, but it figured that out because it has a location tree. Yeah, that's one example. Okay, another example is anytime you browse the web, your browser has cookies, so it's essentially collecting anonymous browser history. Okay? This is again meant for advertising so that they can figure out the types of websites that you go to and give you some ads that are relevant to that website. Okay? Even though that browsing history is collected in an anonymous fashion, okay, there are a number of research studies that have shown that it is very easy to take that information and other public information that's available and de-anonymize the user. So they can actually figure out where you are, okay, based on just anonymous history. Okay, again, that's not the intent when the data was anonymous, but easily de-anonymized. That's a privacy violation. Okay, neither of these examples are security attacks. You can just assume that these are just data collection exercises, but they're revealing additional information that was not intended to be revealed. Okay? And the same is true if you think about machine learning examples. Okay? You can actually take a deep neural network, okay, and simply make requests, inference requests to that network. And based on the output it produces, you can actually learn internal details of that model that is being used to do the inference. Okay? That's a privacy leakage as well, because you are just looking at the model as a black box. You just send it request, it gives you some answers. Now you figure out what's inside. And these attacks have been used to actually figure out sensitive details of large neural networks that are commercially produced and so on. Okay? All of these are privacy violations which have nothing to do with security. Okay? Just as an example to convince you that these are actually different but related concepts, right? So that's all I'm going to say about privacy. We'll come back to security and we'll talk about a few different protocols. First one is authentication. Okay, the reason this is important is if you build a distributed application, web service, and so on. In this class, we didn't put any authentication on this applications you build, but typically you would want to authenticate, have the users authenticate before you let them access the application. Okay, you might have to create user profiles and so on. So how do you authenticate users? You need to basically, you can't just trust the user to tell you that they are such and such, because just as if someone calls you on the phone and claims that they are your bank and asks you for some sensitive information, you're not going to give it to them because you don't know person on the other side is actually the bank or somebody who's masquerading as the bank. So you need some way to figure out who the person is that they claim to be. Okay, that is called authentication. Authentication allows for two parties within that are communicating with each other. It allows the each party to know who the other parties are, verify that they are who they claim to be. Okay? So if usually all of the security and protocols have two parties called Alice and Bob. Okay, so they could be machines, they could be people, doesn't really matter from our perspective. So we are just going to use that example. Okay, so our version 1 of the protocol is Alice is trying to authenticate to Bob and say, I'm Alice. That's a, let's say, username. Okay, Bob can't believe that because somebody else can also say, I'm Alice. How does Bob know that that's actually Alice? So you have to use other ways to figure out that Alice is who she claims to be. So in some systems, you use things like IP address. Okay, so you can say that this is Alice's machine. It has this IP address. So if Alice sends you this message from that machine with that IP address, you trust that that person is actually Alice. Okay, that's not really good way of doing authentication because IP addresses are easily spoofed. Okay, you can just send an IP address, IP packet with a fake address in it. Okay? So the other end is not going to know whether the address that has come on the IP packet is correct or not. Okay? So that clearly, that technique is used in many network services still. It's not a good one, okay? Because it's easily broken. Okay? Third one is, of course, you use a password. Okay? That's how many of our services work. You have a username and password. So your Alice is going to say, I'm Alice, here is my password. Okay? Now you might think that's great, but if this is actually going in plain text, okay, Trudy, who's an intruder, can intercept that packet and essentially learn the password. Okay, and then once you know the password, then you are going to essentially go and use that password to log into this. So many services until maybe 5-10 years ago did not actually encrypt the traffic. Okay, so things like remote login, before SSH came along, there was something called Telnet. Before secure file transfer came along, there was FTP. All of them sent username and passwords in clear text. Okay, so any intruder could figure out the username and password that was being sent by that user. Then your password is easily broken. Okay, so that's not going to work. So there are other ways to do this. Okay, the one is to actually use encryption. Okay, I'm not going to go into what an encryption algorithm is, but I'm assuming you kind of have a high level idea. An encryption technique takes any message in some text, and then it uses something called a key. Okay, and then it generates what is called an encrypted version of that message. And the encrypted version of the message has the property that if an intruder gets hold of that encrypted message, they cannot figure out what the original message was. Okay, you can't do simple brute force attack and try to figure out what was the original message. So if I intercept an encrypted message, okay, then if you use a good encryption algorithm, the intruder cannot easily, okay, with a lot of brute force compute power, you may be able to, but you cannot easily figure out what the original text was. Okay? There are many encryption algorithms. We are not going to go into most of them here, but we will use at least one that I'll talk about on the next slide, which is called public key cryptography. But for now, assume you have an encryption algorithm. What it is not important. Okay? Every encryption algorithm is going to use a key. That key is used to encrypt any message you send, and the same key is needed to decrypt it. Just as if you have a lock, you use the lock, you use a key to lock it and unlock it. The same thing is true here. Okay, we will have an encryption algorithm. There's going to be a key, and then both parties who are trying to communicate need to know that key. Okay, otherwise, you can't if you can't encrypt and decrypt the message without that key. Okay? So here we are going to assume we are trying to still solve the authentication problem. We'll assume that Alice and Bob are going to use encryption for authentication, and they have chosen a secure key. Okay, beforehand that's going to be used for encryption and decryption. Okay, so in this case, Alice is going to send a message to Bob, which is encrypted, saying I'm Alice. Okay, so that's an encrypted message. Okay, only Bob knows the decryption key other than Alice. Okay, so Bob can then decrypt the message and say that it says I'm Alice. So now Bob knows that only Alice would have sent that message because only Bob and Alice know the key. Right? So then Bob will authenticate Alice. If not, you will say that's not Alice. Okay? Now you might think this is good because you might use a really secure encryption algorithm. Okay? But it is not, because what can an intruder do? They can intercept your traffic. Okay? So the intruder can get the encrypted version of this message, not the actual message, but the encrypted message. Okay? What prevents the intruder from sending that message back to Bob to claim that they were Alice? Right? So Trudy can get that encrypted packet and then later on send that same packet to Bob, even though Trudy does not know the encryption key at all. I just got hold of the encrypted packet and I sent here, I'm Alice, here is the encrypted version. And now Bob is going to assume that that's Alice. Okay? This is called a man in the middle attack or person in the middle attack, also called a replay attack. Okay? So in this case, even though you don't actually have the encryption key, you can still break authentication if you use something like this. Is that clear? What I just said? Okay. So that's not going to work. Okay, so we got to make this even better. Okay, so we are getting there. So that's our third attempt. Here's the final attempt. Okay. So we are going to now add to an encryption some sort of a password, okay, which cannot be used for launching the previous type of replay attack. Okay. The kind of password we are going to use is called a nonce. A nonce is simply an integer, but it's also once in a lifetime number. Over the entire course of this application, we are going to use a number and an encryption technique to authenticate. And once you generate it, you will never generate it again. Okay? So it's a randomly generated number, but you will never regenerate it. So it's once in a lifetime. Lifetime is the lifetime of the application. Okay? And we'll call this as a nonce, okay, which is a one. It's also in this case going to serve as a one-time password. Okay? But this is what we are going to do. Okay? So here is version 4 of our protocol. Okay? Alice is going to send her username to Bob. I'm saying I'm Alice, or some unsent, unencrypted. Okay. Bob is going to send back once, and Bob is going to generate a nonce and send it back. So that's a challenge. So here's a number, prove that you are Alice. Okay. So that's going to go unencrypted as well. Okay. So Alice is going to receive this integer, and what Alice will do is that she will encrypt the integer, not her username as we had done previously. We're going to encrypt the integer and send it back. Okay. So Bob gets the encrypted version of the message. Bob decrypts it, make sure that the number that's come back encrypted is the same one that was sent. And now you have authenticated Alice. Okay. Is that clear what I said? Okay, so why can you not launch a replay attack here? Yes. Okay. So first thing is just getting the encrypted version of the packet is not very useful because this is never going to be used again. That number was used in some future time. You could have stored it and presented that as the encrypted nonce, but it's never going to be used. Okay. So that's one. And you don't have the key. So you could not have grabbed this and then generated that encrypted version of the nonce and tried to send that either. Since you don't have the key and the number is once in a lifetime, you can't actually capture the encrypted packet and use it again. Okay? Unlike the previous protocol where you just encrypted the username, there's no password in the previous case, right? You just said, I encrypt a username with a secret key and present it as an authentication of Alice. That didn't work because you could just use that for a replay. Right? Any questions here? Okay, that's essentially version 4. This uses something called a symmetric key encryption, where you need to have generated a key for some encryption algorithm and pre-shared it between Alice and Bob. Okay, we assume that the key is already known and they're simply using it for authentication. Okay, that's first assumption number 1. Okay, assumption 2 is that you are going to assume that the nonce is truly a once in a lifetime thing. You will never be able to reuse it once you generate it. Otherwise, you will be vulnerable again. Okay. Yes, question. Yeah. So your point that is being made is you can add a timestamp, or your timestamp could be your nonce, because maybe if time is advancing, you'll never come back. So yeah, you could enhance the protocol and add some additional features to it to reuse. But this is a simple protocol that doesn't depend on anything more. If you just have a large enough integer and you're generating it randomly, you will assume that you may not ever come back to it. Okay, so that's the simplest one. But yes, you can certainly do other things with this. Okay, that's one protocol. Here's another protocol which uses something called public key cryptography. Okay, so this is a different encryption protocol. Okay, so there are two types of broad encryption techniques. One is called symmetric, another is asymmetric. Okay, in symmetric encryption techniques, there is a single key. The same key is used to encrypt and decrypt. If you encrypt a text with some key, you need that exact key to get back that text. Okay, so that's called symmetric. There's encryption and decryption keys are one and the same. Okay, and then you have asymmetric. Okay, the most common one in there is called public key cryptography. So there are two keys. You can think of them as an encryption key and a decryption key. Sometimes this is also called a private key and a public key. Okay, so when you construct the key, it actually gives you two keys, not one. Okay, so there's a public and a private, or encryption and decryption. Okay, the private key is what you keep with you. Never reveal it to anyone. Okay, the public key you can give to whoever you want. You can even put it on your website. Okay, because that's something you can make public. It doesn't harm you. Okay, but the private key or the encryption key you keep to yourself. Okay, and the idea is still the same. Okay, because there are two keys. You can use one key to encrypt, then the other key is used to decrypt. Okay, so for example, you can publish a public key and somebody wants to send you a message. They can use your public key and encrypt it and send it to you. Only you can decrypt it because you have the other key. Okay, and vice versa. If whatever you encrypt with your private key, can be then decrypted only with your public key. Okay, so here is how our protocol can be now used with public and private keys. Okay, here you don't need to pre-share a key, okay, because in the previous case you have to create that and share it. Here public key is assumed to be known because it's public. You can, as I said, put it wherever you want, put it as an email signature, put it on your website, whatever. Okay, so Alice is going to send the same message. I'm Alice. Bob sends a nonce. So I prove that you're Alice. What Alice will do is she will take her DA, in this case is a private key. Okay, so she will use her private key and encrypt the nonce and send it. Okay, Alice and Bob knows the public key. Bob will decrypt it and say that is indeed the nonce. Okay, so you will extract that message out and know, and then you can be sure that only Alice could have sent that message because only Alice has the private. Okay, public key, anyone can verify that it's Alice because well known. But in this case, it also tells you that only Alice could have sent this. Is that clear? Authentication. All right. So we are going to be done with authentication. Okay. Except for I will also mention that even this technique has problems. Okay, one of the problems is that you can actually impersonate Alice in the following way. Okay, so Trudy is going to impersonate as Alice to Bob. So how can this be done? Okay, so essentially Trudy is going to try to, let's say Bob is a machine. Okay, Trudy is a person. Is going to send username I'm Alice. Bob sends back a nonce. Okay, Trudy is going to intercept the nonce. Okay, Trudy does not know Alice's private key. Okay, so we assume that if you lose your private key, then all bets are off. Okay, so that's not really the problem you're trying to solve. In this case, Trudy does not know Alice's private key, but she does have her private key. Okay, so she's simply going to send the nonce back with her encrypted with her private key. Okay, now Bob has to figure out that this is Alice. So what Bob has to do is go find Alice's public key from somewhere. Okay, so this is where the problem comes. Okay, so Bob is going to try to get the public key, and if that method is not secure, then you have a problem. So for example, if you publish your public key on your web page, okay, that's one way somebody can get your public key. They'll come to your web page and get it. Or you put it in your email signature, they can get it. Okay, but none of these are secure way of distributing your public key because somebody can hack into your website and replace your public key with somebody else's. Okay, or somebody can intercept a message and change the public key to something else. Okay, so here is Bob trying to get Alice's public key. Okay, and then Alice is somehow going to intercept that request and send her public key instead. Okay, so now Bob doesn't know that there's somebody else's public key. You just ask for Alice's public key. You got something, and you think it's the right key. Now you decrypted that nonce, thinking that came from Alice, and now you are essentially in trouble. Okay, you can also break things like SSH with some problems like this if you're not careful. Okay, because there are any public key. So the problem here is not the encryption algorithm or the authentication technique. Both are fine. The problem is that key distribution itself is the problem, right? So if your key is not securely distributed, you are going to have an issue. Okay, you can't keep anything secure, right? So it's like you have an apartment, you want to let your friend in, you put a big lock, but then you put the key under the mat. It's not going to be secure, right? Somebody gets the key, they can enter. Yes, so putting a big lock is the same as having a big encryption. You don't safeguard your keys or secure, distribute it securely. No, you can't actually deal with. So any encryption technique, however so secure, is only going to be as secure as the way you are going to distribute your keys. Whether it's symmetric or asymmetric doesn't matter. That part is broken, then it's not going to work. Okay, yes, question. Okay, question is, why is Bob trying to get the public key? Okay, so if you look at the previous protocol, the protocol is very straightforward. There's a public key and there's a private key. Okay, you have your private key, and whoever you are trying to communicate with needs to have the public key because they need to decrypt it, your message. Okay, so Alice is going to say, I'm Alice to Bob. Bob sends a nonce, and then Alice is going to send the encrypted version of the nonce. Okay, for Bob to verify that the message came from Alice, Bob needs Alice's public key. Okay, so you use the public key and you decrypt the message. Okay, we didn't say how Bob got the public key in this case. We just assume Bob had it. Okay, but Bob has to get it from somewhere to begin with. And if you don't get the right key when you're trying to get it, then you have a problem. Right? That's what we said in the next slide. Right? Any other questions here? Okay, so that is authentication. We are done. Okay, so you got to understand that encryption algorithms are all good, but this key distribution can cause problems. All right, so this I already showed you. I'm not going to go into this. We'll now use this idea to do something else, which is called digital signatures. Okay? We already saw how Alice can not sign really, use the private key to encrypt a message. Okay? So you can essentially use public and private keys also to construct what are called digital signatures. Okay? And so what are the properties you want from a digital signature? Okay? Essentially, there are two things you want. Okay? If you want to sign a document electronically, you want the signer to not be able to claim that they never signed it. Okay? If I show you a signed piece of paper with your signature on it, a physical paper that has your actual signature, you can't claim that that was not you because that's your signature. Okay? And that's the number one. And number two, okay, you cannot actually fake the message. Okay? So that's basically how you want to be able to do. So somebody else can't sign saying they're you. Okay? That's also not something you want. Okay? In the real world, of course, somebody can forge your signature, right? If they're a good forger, then you're in trouble because you can't claim it's not you. But here we don't want that problem. Okay, so you don't want anybody to send a fake signature, and if it's actually signed by you, there should be a proof that that was you, so you can't claim now it's not you. Okay, so how do you do this? It's very straightforward. We can use the same idea. Bob wants to sign a message M. Okay, Bob will take his private key and simply encrypt that message with the private key. Okay, and that's a signed copy of M. The encrypted version of M is simply the message that's signed by M. Okay, and now Alice can first verify that the Bob has signed the message because Alice can take Bob's public key. Public key is freely available, and decrypt the message. Okay, so now since the message is successfully decrypted, you know that only Bob could have encrypted it. So essentially Bob encrypted it as his signature, and you can decrypt it successfully, and Bob has signed that message. And Bob cannot claim to have not signed it because only Bob knows the private. So that encrypted or the signed message, which is the encrypted message, is only something Bob could have produced. Is that clear? Okay. Now that's something you can do with public key cryptography, but yeah, that's quite expensive to do. If you actually use your public key to encrypt documents, you'll see that that's quite expensive because public keys are supposed to be very secure, so they're really long. Okay? The longer the key, okay, the more compute intensive it is to encrypt something. Okay? The cost of an encryption and decryption algorithm is actually determined by how long the key is. Okay? The more secure you want to make the algorithm, the longer the key needs to be. Okay? The reason the key needs to be longer is that longer keys are less susceptible to brute force attack. Okay? Because the biggest problem for any encryption algorithm is I try all keys. If one of them works, I'm done. Okay? So if you have lots of compute power, you have lots of GPUs, okay, you can just try all your keys and something will work, and then you say, okay, I found the key. So to prevent that, you want longer and longer keys, which means that it's harder and harder to try brute force attack. There's simply too many keys to try. Okay? So since that is a good property for an encryption algorithm, all secure ones use very long keys. Okay? Long keys essentially also means expensive to encrypt and decrypt. Okay? So if you're going to take a long document and try to sign it with your private key, it's going to take you a long time. Okay? It works fine, but it's just expensive. Okay? So we want to reduce the overhead of our signatures, okay? Even though this is a fine approach. Okay? So what can we do? Okay, we will use an approach called a message digest. Okay? Because encryption and also decryption of entire messages using digital signatures is expensive, we need a better way to do this. So what are we going to do? Okay? The first thing is we are going to say, rather than signing a long message, let's sign a shorter version of that message, okay, representation. So we can use a hashing function, okay, and take that hash function and construct the hash of that message. Okay? That's one thing you can do. Okay? Now, what you can do is rather than signing a very long document, you are going to just sign the hash of the message itself. not the document. Okay? Even though your key is long, if the message is short, it's still okay. If your long key and long messages, that's really very expensive. Okay? So let's try to sign a shorter version of the message. Okay? So we sign now the hash of the message, that should be capital M, H of M, rather than signing the original message itself. So now you have the original message, not encrypted. You have a signature. The signature is the hash of the message that you then encrypted with your private key. Okay? So H of M, which is the hash of message M, is the thing that you're actually going to sign. Okay? Yes, question. Okay, question is easier. Is it easy to brute force? So let's ask what that even means. So first, let's do the following thing. So what is the property you want from the hash function, okay, that can cause you to have issues? So for example, if I give you a hash of a message, the first thing is this should have the same property. Somebody can take your public key, okay, and then they can extract the hash, because they can decrypt this message. You got the hash back. So then to verify that you signed it, you got to take the original message and actually hash it again and compare the two hashes. If they match, that means that you signed it. Okay? The hashing function is public and it's well known, so you don't need, that's not a secret. Okay? So anyone can do H of M, given a message, I can compute the hash. Okay? So I can decrypt this, I can recompute H of M, I compare. Okay? That's how I'm going to verify your signature. Okay? Now, what problems can you cause? Okay? If I give you a hash H of M, okay, if I can construct some other message that gives you the same hash, okay, then I can claim that you signed something else. Okay, is that clear? What I just said? Because hash functions are not perfect; they are going to have collisions. Okay, two values, when you input them to the hash function, can produce the same hash, because that's how hash functions work. They take a longer message and they give you a shorter hash. So there are many strings that will map to a smaller hash value. Okay? So if you have signed some message that generated a hash H of M, that's some integer, if I can brute force construct some other arbitrary document that gives me the same hash, I can claim that you signed that other document. Okay? Good hash functions will not allow you to do that. Okay? It should be infeasible. Given a digest or a hash, it should be infeasible to find some other string that produces the same hash value. So this requires that you use a good hash function, otherwise that's going to cause problem. Okay? And so you shouldn't be able to find two messages X and Y that produces the same hash. Okay? So if you use good hash functions, this is still okay. There's no problem in that regard. Okay? The only brute force thing you can do is try to generate a message that will give you the same hash value. But if you have good hash function, that should not be possible. Okay? Is that clear? So digital signatures actually use this. Okay, so you can actually set up secure email in your mail client. If it supports that feature, you have to put in a public and a private key. Public key, of course, has to be sent to whoever receives it, otherwise they can't decrypt it. But you can sign all your email. Okay? What it will do is it will take your email message, it will generate a hash, okay? And then it will essentially take the hash and it will sign it with your private key. And that is attached to the document. So the email itself is not encrypted in this case. You're just attaching a signature that can be used to verify that the mail actually came from you. Nobody's spoofing you as the email. Right? So that's what you can actually do if you want to use this in email. But of course, you can sign any document. It doesn't have to be email. Okay, using this method. A lot of electronic contracts use this type of idea to sign electronically. Okay, any questions here? Okay, that is message digest. I'm going to talk quickly. You have a question? Okay, all right. So I'm going to quickly talk about two hash functions. We don't actually have time to go into details of these, but I just want to explain some of them. So there's a one called MD5, Message Digest 5. Okay, it essentially used you can take a large message and then you can use that hash function. It will generate a fixed size hash value. Okay, and it was a very popular hash function, but it is no longer secure because you can brute force it. So you can actually construct some arbitrary string that gives you the same hash value, because even this hash function uses some a key size. It's not encryption. It still uses a key size that's small enough that you can then try other strings and try to figure out some other string that gives you that same value. In other words, you can actually break the sec property that's mentioned here. So it's not considered to be secure anymore. So MD5 still, you might see that some places still use MD5, but not really the right thing to do anymore because it's not secure. So there are other family of functions. Okay, one is called SHA, stands for secure hash function. That's a family of hash functions, not just one. And you can essentially use 160-bit hashing. You can now use 256-bit hashing. That's called SHA-256. 512-bit hashing. That's 512 bits to do the hash function and so on. Okay, again, it's not encryption, but even hash function use a key to generate a hash value. Okay, the longer the key, the harder it is to actually violate the hashing function feature, which is collision, probability of a collision and probability of finding an arbitrary message that gives you the same hash value. So neither of those you want to happen. Okay? So the hash functions have also grown in size in terms of their essentially key length. Okay? So this is what is actually used today. If you see anything that uses hashing, you will see that it probably uses some family of SHA to do some to do whatever it's trying to. Okay, so this was developed by the U.S. government, and the hash function is actually public, so anyone can use it using a library. Right? Okay. Any questions on hashing? Okay. So last thing I'm going to talk about is we were mentioning this problem of key distribution, right? Because you remember I said Bob is going to look for Alice's public key, and then Trudy just sends a key of hers as impersonating as Alice's key, and then you are essentially going to cause problems with authentication. So what can you do to prevent all of this? Okay. So first thing, there are many methods. One is to essentially use a trusted server, which is called a key distribution center, KDC. Okay. So what you do in the key distribution center is you deposit your public key with the key distribution center. A private key is your own. Okay. Your public key you deposit with the key distribution center. So if you want to go and retrieve somebody's public key, you go to the key distribution center, and we assume that that is a secure place to store it. Okay, so it's not going to get stolen or anything like that. So, and you can trust that whatever is coming back to the KDC is essentially the right key. Okay? So that's one approach. You use an intermediary to distribute the key. Okay? Everything else is the same, whatever we talked about. But this is just saying that I distribute public keys in a secure way. I don't put it on my website, because then if somebody hacks my web page, then they can replace the key. Then somebody else can impersonate me, because then the people who come to my website is seeing somebody else's public key, and then you can sign things, etc. So that's bad. Okay? So here's an example of how key distribution can work. Okay? So here you have Alice on one end, Bob is on the other. What is in the middle is our intermediary, which is our key distribution center. So in this case, we can use key distribution center for many things. You can use it to distribute public keys, but here we are going to use it to generate a symmetric key that Alice and Bob can use. But we will use public key cryptography to but to sort of boot up the session by generating a session key. Okay? So here is how Alice is going to initiate the protocol, saying, I'm Alice, I want to communicate to Bob, construct a session key for us. Okay. So, and we will assume that Alice has a private key and the public key is already stored at the KDC, and we trust that. And Bob has done the same thing. Bob has his private key, public key is stored at the KDC. Okay. So what the KDC is going to generate a session key, which we have called KAB. That's a key that Alice and Bob will use for just that session. Okay? Not a public key or a private key. It's a special key for some encryption algorithm. So you construct that, and then you essentially encrypt that with Alice's key, okay, and send it over. So Alice cannot decrypt that key and get the session key. Same thing can be done here. The KDC can send a message saying Alice wants to communicate with you. Here's a session key I generated and sent to Alice. So now that session key has come to the other end. So both parties now have a key. Okay? In this case, you're using a symmetric key, but the KDC generated it for you, and you trust the KDC, so bad things cannot happen. Okay? Because again, if you generate a bad key, somebody else gets hold of it, and even though you may be using a good encryption algorithm, all bets are off. You have a person in the middle attack and all these kinds of problems. Okay? So that was one approach. Here's the same technique where the KDC is only going to communicate with Alice. In the previous case, the KDC sent a message both to Alice and Bob, but Alice wants to initiate the communication. Here is what you can do. Same idea. If you're going to send a message to the KDC, I'm Alice, I want to communicate with Bob, construct a key. Okay? So you construct a session key, KAB, and you send two messages to Alice. One is encrypted with her public key. The other is encrypted with Bob's public key. Okay? So Alice will use her private key to extract KAB. Okay? And then she is going to take the other part of the message, which only Bob can decrypt because it's encrypted with Bob's public key, and send it to Bob saying, I'm Alice, here's a session key. And then Bob can extract the session key, and then all messages can be encrypted. Okay? And there are many different variants of this protocol, but this is just a very simple one that shows you how key distribution is used. Is that clear? Okay. All right. So I'm going to not go into the Needham-Schroeder protocol. It's a more complicated approach that uses nonces. It's the same idea, but adds a nonce, which is the R in there. We will ignore that. Okay? That also gives more security. Okay? So here is an approach that does not use a key distribution. Okay? So let's say you don't want to use an intermediary. Alice and Bob want to generate a session key themselves. Okay? So you could ask, why do you need a session key if you have public key cryptography? Okay? Why can't I just use the private and public key to communicate? Why do I need to have a session key? Yes. Yeah. So as was just mentioned, you could use public and private key to encrypt and decrypt messages, but it is very expensive. There's a lot of compute overhead that you are going to incur. So the best, not the best, but a better approach is to use public and private keys to first generate a session key and exchange it, and then use the session key for actually communicating. Okay? That, as we'll see in a little bit, that's how you actually use SSL, and this is how you use HTTPS. It uses public and private keys to generate a key for that session, and then you use a somewhat less expensive encryption algorithm, still pretty secure, but less expensive. Okay? Because if you use this more expensive one, then you are going to spend a lot of CPU resources just to encrypt and decrypt messages. So here's how it's going to work. Okay? Alice is going to send a message to Bob saying, I'm Alice, here is a nonce. Okay? So this RA is a nonce. Okay? That just means it's a once in a lifetime number. And both of those pieces of information saying, I'm Alice, here is a nonce, is encrypted with Bob's private key. Okay? So that's this key here, A plus B. Okay? That's Bob's private key. So only Bob can decrypt this message, because Bob only has the private key. Okay? The message comes to Bob. Bob decrypts the message saying, okay, this Alice trying to communicate with me. He sent a nonce. Okay? And Bob is going to send back a message saying, yeah, I'm sending your nonce back, so you know it came from me. Okay? And then Bob is going to send a second nonce, which is RB. Okay? And Bob is also going to create a key in this case. Bob generates the key and sends it. So you say, here's your nonce back, here's a second nonce, here's a session key that we are going to use. All three of these pieces of information will be encrypted. In this case, it will be encrypted with Alice's public key, so only Alice can decrypt it. Okay? So that message goes back to Alice. Alice decrypts the message. First says, okay, the nonce came back, so this is actually Bob. Okay, nobody's impersonating Bob. There's no replay because once in a lifetime message. Okay, then you get back the second nonce. You get the session key. So then what you do is you will take that nonce, you'll encrypt it with the session key, send it back. So Bob can figure out the nonce came back. So you send nonce both ways to prevent replay attacks. Okay, and you also generate a session key in the process that you exchange. Okay? So now both Alice and Bob have the session key KAB. They figured out that they authenticated each other because they used the nonce. Okay, because using the same nonce idea that we had, you're doing mutual authentication, which means each of them is authenticating to each other, so you know it's them. And then you use the session key. That's what you use for all further message exchange, which is not shown here. Okay. Any questions here? Okay, that's called public key exchange. Okay. So now, as I was mentioning earlier, you essentially have to distribute the public keys in a secure fashion to begin with. Okay. If your public keys are not sent securely, you have trouble. Okay. So you can again use a key distribution center to store all the public key. Every time you want to communicate with someone, you go to the KDC and say, give me such and such person's public. Okay. And you get it from them, and then you now have that person's public. That's one approach. Okay. But every communication between pairs will now involve a third party, which is the key distribution center, which is a repository of your public keys. Okay. Now, what if you don't want to have the public key come from the KDC, but you still want to know that it is the right public? What can you do? Any thoughts? You probably heard of these terms, but you still need somebody to tell you that it's the right key. So you can't just go to some random website or something like that and try to extract someone's public key. So you need a trusted intermediary, but you don't want to go every time and say, give me such and such person's public key. Okay. So what we are going to do is we are going to tell the trusted third party to essentially sign the public key. Okay. That's called a digital certificate. Okay, which you've probably seen when you go to a browsing session, when that lock turns green and you do HTTPS, that usually means you set up a secure connection. But if you click on that lock, you will actually open a window. It will show you the certificate that came. Okay, so what is a certificate? A certificate is essentially a public key of some entity that's signed by a trusted third party that both you and the other party trust. Okay, so there are signing authorities. They are called certification authorities. They will issue a public key and they will sign your name saying you are such and such person or you are such and such machine and this is your public key. And they'll sign it with that certification authority's public key. Oh, sorry, private key, not public key. Okay? And we assume that the public key of the signing authority is already well known. So it's built into browsers. Okay? If you actually go and look at the security tab on the browser, it will recognize several certification authorities. All that means is the browser shipped with all those certification authorities public keys already. Okay? So when a certificate is presented to you, okay, you can simply use the certification authority's public key to decrypt it and say, yes, now I can see that it says the person's name and it shows me their public key. So I can now, since I trust the certification authority, okay, I can believe that it's the right public. Okay. So if you do this, all you have to do is whoever is trying to communicate with you has to get a certificate, okay, already signed, and then you just present the certificate. Okay. You don't need the key distribution center or the certification authority to give you the public key. The public key is already distributed and is signed by a trusted third party. Okay. So what will happen in this case? Okay, you have a trusted server. Okay. The certification, that's our certification authority. It will generate a public key. It will sign it with the certification authority's private key and distribute. So all that you have to do if you're Alice is say, I'm Alice, here is my certificate with my public key in it. Okay? So then Bob can doesn't have to go looking for Alice's public key. Alice can provide it. It's a signed version of a public key. Bob can verify that that's actually Alice's public because it's signed by somebody Bob trusts. And we know how to do signatures already, right? Is this clear, what I said? Okay, so Trudy can't send her private key or her public key claiming to be Alice because you can't get a certification authority to give you bogus certificate, okay? Claiming to, because certification authorities are supposed to verify before they give you a certificate in somebody's name. Okay? They just don't, you can't just say, I'm such and such person, give me a public key. Okay? They'll verify your name and whatnot before they issue it. Okay. So that's what you are going to essentially use. And in this case, if your private key gets stolen, So maybe you lose your laptop and your private key is stored on it. Now you are in trouble because somebody can get your laptop, get your private key. The public key is well known. You can start impersonating someone. Okay? So that can be prevented because the certification can be revoked. Okay? So you can actually, the certification authority can take a certificate that's been already issued and revoke it. This happens whenever there's security problems. So old certificates get revoked, new ones get generated, and then your browser or whichever entity is trying to verify it knows that it's a revoked certificate because they might have a list that they've stored or what. Okay? So certificates can be revoked, so it can avoid problems where your private key gets stolen because your machine was stolen and your private key is stored on it. Okay? Is that clear? So this is essentially going to be the basis for creating applications, your distributed applications that can securely communicate. Okay? You will need to encrypt your communication, which you didn't do. You send your gRPC calls or HTTP requests all unencrypted. Okay? None of that is actually secure, okay? Because anyone can see those messages going back and forth and then figure out what's going on. So you want to essentially do authentication, which means if a user is using the application, they need to verify themselves. Okay? And if components of your applications are talking to each other, no user involved, they still need to use encryption and things like that. Okay? This is the basis for building security into your distributed application. You're going to essentially lose public key cryptography, you're going to create session keys, you're going to communicate, you'll use certification authorities to prevent bad public keys from being distributed, claiming to be somebody else and things of that. Any questions on this? Okay, so now we will, I'm going to skip some of this, but we'll talk a little bit about how these basic concepts can be used to implement security in modern networks, enterprises, and so on. So just encrypting and doing authentication is just one part of the picture. But if you look at any modern enterprise, you will see that there are lots of different elements that are used to implement security of all sorts. Okay? There is something called a firewall. Okay? That's a machine that sits at your network. So it's actually examining every packet that's going both ways, coming from outside into your network and going out. Okay? And you can essentially use firewalls to prevent certain machines or certain IPs from sending packets. And so maybe there's an adversary that's trying to attack your machine. Okay? You can just take their IP address and you put it in the firewall and say deny all traffic from that machine. Your firewall will just block any packet that comes with that IP address. So they can no longer send traffic into your network. Okay? You can also do it the other way. If you want to block certain machines from accessing external services, you can also put rules in your firewall that prevents that from happening. Okay? That's used to implement very basic network security. No encryption or anything like that. There are firewall rules that say what is allowed, what is disallowed. Okay? And then you have more sophisticated firewalls that are called deep inspection firewalls. Okay? So they do deep packet inspection. So they will not just look at the IP address, which is the header of the packet. They'll actually look inside the packet to see if there's anything bad in it. Okay? One example is you look inside the packet for malware or virus signatures. Okay? If whatever packets are coming in, if the data in the packet actually has known viruses or bad thing, you can scan the packets, not just the header, but actually scan the packet to figure out if there's any bad content in the message. If so, you can block those packets at the firewall itself, not even let it in. Okay? Now these firewalls are more expensive, also more intrusive. Okay? The first one was just looking at the header. Every IP packet has at least 4 pieces of information: IP address, source port, source IP, source port, destination IP, destination port. You probably know this because you wrote all kinds of distributed applications. Right? So standard firewalls only look at those 4 pieces of information and decide allow the packet or disallow the packet. Deep packet inspection firewalls will look at those. They'll also look inside the packet. Okay? So they'll scan every packet that goes through. Okay? And then you have other things that there are email virus scanners where you're only looking at emails. So every email that goes through, you look at the attachment and see if there's anything bad, or you can even scan the contents and say, is this spam? So those are the ones that are actually going to do additional filtering, but that's only for certain types of applications like email. Okay? Those are all network traffic-based security techniques. Okay? You can also have network isolation through this technique called VLAN or virtual LAN. So think of a virtual LAN as taking one LAN or one wire and essentially constructing multiple LANs on it. Just as we virtualized machines using VMs, you can also virtualize networks using virtual LANs. Okay? So if you're a machine that gets placed into one virtual LAN, you cannot see traffic or machines in another LAN, even though they're part of the same physical network. Okay? So the way you're going to do this is you are going to group IP addresses into a LAN group, and only those machines can talk to each other. Even though there may be other machines on exactly that same LAN, they can neither see each other nor can they communicate with each other. Okay? This provides you network isolation. Exactly the same as when you have two VMs, one VM cannot look inside another VM, or you have two containers. If you are a process in one container, you can't actually see what may be outside. You're isolated and you're prevented from seeing what else is on your machine. If you have VLANs, you're isolated from seeing what else is on your network. Okay? Same kind of concept is widely used for both security and resource allocation and so on. Okay? There's something called radius servers. Those actually store passwords. That's how you're going to authenticate to, let's say, Wi-Fi. Okay? Wi-Fi traffic is also encrypted. If you use good Wi-Fi, unencrypted Wi-Fi is really not what you should use. And there are other things like VPNs, which are virtual private networks that allow you to connect to a network from outside using a secure channel. You can use SSL and whatnot. We'll talk about those. Okay? So all kinds of techniques. Okay? So security is big business because there are all kinds of adversaries that are trying to launch all kinds of attacks. So no longer possible just to say I'm going to encrypt my traffic, I'm done. Okay? You got to prevent people from breaking in, doing all kinds of bad things. Okay? And then a lot more other things when you use web applications and distributed applications. So when you log into websites, it's going to first use SSL to encrypt the traffic. It will make you authenticate. You may use multi-factor authentication, so it will send you a password on your phone or through an app. It may use a CAPTCHA to make sure it's not a bot trying to log in. All kinds of headaches if you run website these days to prevent problems. Okay? You can use challenge response authentication, which is essentially now become more general as multi-factor. Okay? In multi-factor authentication, you need to use two pieces of information to authenticate yourself. You need a password, okay? And then you need to provide a one-time code, which is like a one-time password. Okay? Either the code is sent to you to a phone, or you use an authenticator app that's going to keep generating a new code every 30 seconds, and then you have to provide that. Okay? So it's no longer possible to just use one piece of information, because passwords, people don't use good password. Okay? They'll use something that's their pet's name or their birth date or some piece of information that's easily guessed. So you need a second piece of information. Okay? So even if somebody guesses your password, they still cannot get in because that second thing is not with them. Usually that's used, a mobile phone is used to send a password to your phone or something like that. Okay? So that's essentially two pieces. Now the latest way to get rid of all this is to not use passwords at all. So there's something called pass keys that's just came out actually. Google has just started supporting pass keys. No longer uses password, no longer uses phones. The machine itself is generating secure codes and authenticating. Okay? So you just have to download a pass key, and then you present the pass key and your machine, and that machine will authenticate with each other so long as your phone which is storing your pass key. Okay? So I won't go into that, but they are trying to get rid of passwords because essentially people are not good at choosing secure passwords. So let's get rid of that altogether, use a different approach. Okay? So all kinds of additional problems that you have to deal with even after you use encryption, because of authentication is not great if you use things like password. Okay? So I'll just stop there as far as the set of techniques is concerned. Let's look at this in a little more detail. Okay? Here's a picture of a firewall. Okay? The way you want to think about this is simply a machine. Think of it as a computer that has two Ethernet cards. Okay? One Ethernet card actually connects to the internal network. The other Ethernet card connects you to your internet, maybe to your cable modem or something like that. Okay? So you have two cards. One essentially connects to your network. So here is a card that's connecting to your internal network. Here's a card that's connecting to your external network. And the assumption is all traffic, okay, has to flow through this machine. When traffic comes from outside, it goes through here to the internal network. When traffic is going out, it goes from here to your external network. Okay? Now, what does this firewall do? Essentially, it's going to look at every packet that is going in and coming out. Okay? That's essentially called packet filtering. Okay? So all internal packets are filtered, all external packets are filtered. And the filter simply says, I'm going to look at every packet. And as the name filter suggests, some packets will be allowed and some will be disallowed. Okay? And you as an administrator, okay, of the network get to decide what rules to put in your firewall that say what is allowed and what is disallowed. Okay? The default is everything is allowed, nothing is disallowed. So all traffic is just flowing in and out. Okay? But then you might say, I don't want to essentially get traffic from known malicious bots on the network. So there may be a list of IP addresses that are simply blocked from sending you packets. If those packets come in, your firewall will match that packet saying, I don't, there's a rule here that says that IP is disallowed from sending traffic. You'll just drop it at the firewall. Okay? So you can configure all kinds of rules to say what to do, what to not do. You can also do it for internal traffic, saying during the day, you cannot browse the web. Many employers put all kinds of rules like this. So port 80 traffic going out may be blocked, okay, to certain websites. Maybe not all, because maybe some things are allowed. They might say we'll block whatever social media websites. So employees are not just doing something that is not related to their work. Okay? So that can be done. You can filter packets both ways. And then there's a box in the middle which is called application gateway. That's not looking at packets, but is doing more additional processing. Here, you can put a virus scanner that's looking at email traffic, or you can essentially put a deep inspection firewall that will look inside the packet to see are there known signatures in the packet and whatnot, and then drop additional. Okay? So that requires more heavy-duty processing, so it's not done in the packet filtering router, but done at a higher level. Okay? So that's a simple picture that shows you how a firewall is going to work. Okay? Something that you might actually know. If you have a home router from a cable company, it might have a firewall built into it. And you can actually go and add more rules if you want, or at least you should see what rules are in it already. Okay? So I'm going to skip this and talk a little bit about access control. So that's one technique that is used. Okay? Second thing is to have access control. Okay? Access control essentially says who is allowed to access certain resources and who is not allowed to access certain resources. Okay? We already saw some simple version of this when we talked about file systems. Okay? Every file system has some ability to control who can read or write files. Okay? The Unix file system, file is owned by a user, then the user belongs to a group, and then there's everybody else. So you can have read, write, execute permissions set for each of those two groups, user, a group that the user belongs to, and world. Okay? But if you look at something like a Windows file system, there's something called an access control list. For every file, you can attach a list. The list is all the users who can access that file or not access it. Okay? So when somebody tries to access it, you can go and look at the list and say, is this person allowed or disallowed? Okay? This notion of access control list is actually a broader concept that can be used to control access to any resource, whether it's a machine, a web service, files, data, databases, whatever resources you have. If you want to restrict access to it, okay, one way to do it is to make a list of users who can access it. And if you want to access it first, you have to be matched again then. That's one approach, okay, or access control list, or ACLs. Okay? A complementary approach is something called a capability. Okay? A capability is assigned to a user and says what rights do you have to access resources on the network. Okay? Access control lists are attached to resources. Okay? They have a list of users. Okay? Capabilities are attached to users. They have a list of resources you can access. So it's complementary. In one case, you show up as a user saying, I can do these things. Okay? And so you are allowed or disallowed. In another case, you go to a resource, the resource has a list, and if you are in that list, you are allowed to access the resource or not. Okay? So either one can be, they are both complementary, but these are ways by which you can control access. Okay? Nothing to do with authentication, but just a way to access limit control. Okay? So let me now talk a little bit about secure email, and then I have a couple more slides and we'll wrap up. Okay. So this is an application now to show how we can take all the techniques we talked about and put it together. Okay. So let's say you want to send email securely to someone else. Okay. First of all, email is not secure. Anything you send, anyone who actually gets access to network traffic can read your email. Okay. But let's say you wanted to send it securely. So what does it mean? Okay. First is you don't want someone else to read your email. Only the intended recipient should be able to read it. That's the first property you want. The second property you want is, so that's called secrecy. Okay. Second property you want is to authenticate yourself to the other party. So when your receiver receives the email, they need to know you sent it, not somebody else spoofing you. Okay. That's sender authentication. Okay. Third thing you want is message integrity, and nobody should be able to alter the email in transit. Okay. I send some email, even if it's encrypted, I just cut off some part of the email. Okay. Now what is gone is not really what was sent. So you should be able to know if the message was altered or not. That message integrity. The fourth is receiver authentication, that you need to know that only the intended party can read your message. Okay. So you want four properties. Okay. The message should be secret, it shouldn't be altered. The sender and receiver should be confident that only they can, whoever is sending, they can authenticate each other. Okay. So we can use the techniques we learned to just do all of this. Okay. Secrecy, we know how to do. Okay. You can use your public key to encrypt any email you send. Okay. Rather, you should use your private key to encrypt, not your public key. The public key will be used to decrypt the message. Okay. So you will use public key cryptography, but you will use private keys to encrypt the message. Okay. But normally you want to generate a session key to do this because that's too expensive. So here's an example of how you will do it. Okay. Alice wants to send an email to Bob. Alice is going to generate a key, okay, a session key K. Okay. Alice will then take the message and the session key and encrypt. Okay. The message will be encrypted with the session key. Okay. And then the key itself will be encrypted with her public key, or rather private key. I keep saying public key, with their private key. And this whole thing is going to be sent to Bob. So Bob can now use the key to decrypt it, okay? And then to extract the key, and then use that to decrypt the message. Is that clear? So just to repeat, you want to send a message to Bob, you generate a symmetric key K. Okay? And first encrypt your message, so the message can't be read by anyone. Okay, but now you have to transmit the encrypted message and you transmit the key. Okay, so for Alice to send the message to Bob, Alice will take Bob's public key and encrypt it with the key and send those two pieces of information. So Bob will decrypt it using his private key, so the key comes out first, and then use the key to get the message. Okay, so this is going to ensure secrecy, but it is not giving us some of the other properties. Okay, you don't know the message came from Alice. Okay. So you have to add a signature to this message. Okay, so here is how you are going to start signing the message. So we know how to do signatures already. You have an email you want to send to Bob. Okay, you want to generate, take a hash function. Okay, and you are going to get a hash of the message. Okay, and then Alice is going to sign the message. Okay, so now I am sending a message. It's a signed email. Okay, and we already looked at how to do signatures. So you will now, in this case, send the message as is and send the signature to Bob. Bob can essentially extract the hash, assume that you know the hash function to compare them and know it came from Alice. Okay? So this is giving us authentication and message integrity, but the message is going unencrypted. Okay? It's not secret. So we want to take this idea and the previous idea and combine them to get all four properties. Okay? So here is our entire thing. So we take a message M, that's your email message, construct a hash. Okay, that's the hashed version of the message. Okay, and then you sign the hash. You, as in Alice, is going to sign the hash. Okay, and then you are going to take the message itself and the signature that gives us a new message M prime. Okay, that's something you want to send encrypted. So you generate a symmetric key. Okay, K, and then you'll take this whole thing. Okay, and you'll encrypt it. So now everything is encrypted with the session key. Okay? And then you will take the key itself, you will encrypt the key with Bob's public key, which you know. Okay? So now what is going to be sent is essentially the key itself, and the key is here, and the message that you have essentially encrypted with it. You send an encrypted message and the encrypted key. Okay? So first you decrypt the key and then you decrypt the message. Once you decrypt the message, you will get the message and the hash, and you verify the signature. Then you know that it came from Alice. Okay? So that's basically all the ingredients of making email more secure. Any questions on this? All right. So we have 5 minutes. I'm going to talk about a few different concepts. So I'll talk quickly about secure sockets layer, or SSL. Okay. All of you know how sockets work by now. Okay. We've kind of beaten it to death. So let's see how to make it secure. Okay. So here is how your browser is going to set up a secure socket. So secure socket just looks like a normal socket, by the way. Okay. So you will just, as an application, get a socket handle, and you can simply send messages. You don't need deal with any encryption, decryption. Okay? You just send a message on a socket. The socket library is now responsible for encrypting it, sending it, and the other end, the socket library is responsible for decrypting it. So the application is simply going to get the message you sent, but your socket library has encrypted everything in the path. Okay? So think of it as a socket that you used, except that internally it's doing all the encryption for you. Okay? So how are you going to do this? So we'll use the concept of a browser wants to set up a connection with the server. Normally you set up an HTTP connection, not encrypted. HTTP is not encrypted. Everything you send, the get and the responses can all be seen. Okay? So if you want to encrypt HTTP, you are going to use HTTPS. That's simply HTTP running over secure socket. Okay? So here is how it will work. The browser is going to connect to the server and say, let's do SSL. Okay, server will say, yes, we can do SSL. Here's my certificate. Okay? Because the server has to give you the public key, otherwise nothing is going to work. Okay? And since you have lots of servers, you can't assume you stored all the public key beforehand. So you'll ask the server for a public key. Is going to be given as a certificate, which means the public key is encrypted by and signed by a certification authority. Okay? So the browser has a list of certification authorities, and so it will essentially use the public key of the certification authority to extract the public key that's inside the certificate. Okay? Now, if you have a certification authority you don't know, the browser will throw an exception. You might have sometimes seen an exception saying, I don't recognize the certificate, maybe not a good idea to proceed. If you proceed, then you are taking a risk that you are using a certification authority is not recognized. Okay, but let's assume it's a known certification authority. You extract the public key. Okay, at this point, the browser knows the server's public key. Okay, so the browser is going to generate a session key. K. Okay, it will then encrypt the session key with the server's public key that came in the certificate. Okay, and it's going to send it back. Okay, future messages will be encrypted. Here is the session key we are going to use, which is encrypted. Okay. And then the other end will actually be able to extract that key because it is encrypted with the public key, and then send a message back saying, yes, I got the key and let's start the session. At this point, there's an encrypted channel that's being set up between the browser and the server. Then you just send a regular HTTP request over it. Okay? So it just looks like a normal socket, but you have to do all of this to set up the encryption. Okay? Any questions here? All right. So ignore Kerberos. I'm going to say a few words about electronic payment and then stop. So essentially, we don't have time to go into crypto payments today, but I might spend a few minutes next time to talk about it. But let me talk about electronic payment. Okay? So electronic payments essentially says, how can we use the concepts that we learned to essentially create digital currency? It's not cryptocurrency like Bitcoin. That's also a form of digital currency, but something simpler. Okay? So what is that simpler thing? So let's just see how current payment systems are. So if let's say you are using cash, how is that going to work? Okay, the person who wants to use cash goes to their bank, gets some money, you withdraw some money from the ATM, and you go and give that cash to somebody else, and they can then do whatever they want, spend it again, put it in their bank. Okay? And cash gives you anonymity, because when you give something, pay somebody in cash, they don't need to know who you are. You can go to a store, buy something, they will have no record of who you are. Okay? So that's one approach. Okay? You could also write a check. Okay? So that's going to work as follows. Your bank is going to issue you a checkbook. Okay? You go to the payee and write a check. Okay? The payee is going to go to their bank, deposit the check, and then your bank and the payee's bank is going to run a settlement process where their bank will present the check to you. Your bank look at the check, verify your signature. If it matches, they'll make the payment. Okay? The payment is actually now happening between the banks. You just issued a check, and that's an instruction to the bank to pay this person so much money. Okay? Essentially, that's how checks work. Here's how credit card works. Similar process. Your bank issues, or a credit card company issues you a credit card. Okay? You go to a payee, you show them the credit card, they will essentially authorize a transaction on the credit card. Okay? And then your bank and your payee's bank run a settlement process saying this, this person has essentially said they would pay me so much. Now, between this settlement process, usually are third parties. These are companies like Visa and MasterCard, American Express, that are issuing the card. They run the payment network that allows you to actually make the payment. But if you ignore the intermediary, really your bank and their bank is going to just do the settlement, then you eventually get a bill to pay at the end. Okay? Now, both of those latter things are not going to be anonymous, but either checks or credit card are going to leave a trace. Okay? Cash is anonymous. So can we construct a digital version of a coin that gives me some of that property? Okay? So I'm going to just spend 1 minute talking about this, then we will continue next time. So here is an approach to do this. Right? So you go to your bank and say, rather than withdrawing physical cash, you say, give me $10 of digital cash. Okay? Your bank will essentially give you a token that they have signed. So the bank will say it's $10 and they've signed it, saying it's $10. Okay? So you can then essentially go and present that coin to someone else, and that someone else can go back to your bank and say, here's $10 that you signed, pay me. Okay? And then your bank has to verify that they actually issued that token and then give you that money. Okay? Now, in this process, if you assign a unique number to each coin, let's say you number the coins and assign coin number 1, 2, 3, 4 was issued to such and such person, okay, and you signed it, when it comes back, you can trace it back. Okay? It's no longer anonymous. That's one way to do it. Okay? Prepaid cards, that's how they work. Right? So there's a card number and there's some money attached to it. So what you want is an additional process that are going to essentially blind who it is that you issued it to. Okay? So there are versions of cash where you generate a coin, which means here's $10, here's a number, you blind it, which means you essentially put a piece of tape on the actual serial number, okay, and you send it to the bank. The bank will sign the blinded coin, not the actual coin. Okay? So it's like you took a $10 note, you put it in the envelope, you tell the bank sign that envelope. So they don't actually know the serial number of the note. Okay? Same thing is. So then you get the signed blinded coin, you unblind it, that's what you pay here, and then they go back. And all that the bank knows is they signed it, so they can verify that they signed it and pay the person. Okay? So if you use this blinding process on cash, then you can actually get the properties we had previously, which is anonymous cash that is digitally signed, so you can verify that it's actually real money. Okay? So this is called eCash. Okay? Not used because everyone uses Bitcoin, but that's how all of this came about. Okay? So we'll stop here. Next time we'll spend 5 minutes talking about